We're standing now in the foyer of the Imperial College Carbon Capture Pilot Plant in the centre of London. This new facility is a result of a 2-year collaboration between Imperial College and a range of industrial partners, including ABB. Our new pilot plant has been designed to allow us to train the next generation of young chemical engineers who come from all over the world to study at Imperial College. The 12-metre high, £2 million facility has a fully functioning carbon capture plant. It incorporates leading-edge technologies, the sort of technologies that will become common in the future industrial landscape of the UK. The pilot plant is part of a £9 million ChemEng Discovery Space facility, which has an emphasis on hands-on and laboratory-based teaching and learning. As to having a specific carbon capture pilot plant, well, it's all down to climate change, of course. The topic has taken centre stage in the eyes of the world, driving innovation, helping develop new processes and creating new markets for the types of professional skills that we here at Imperial are pleased to provide.
Carbon capture works by passing a CO2-rich gas mixture, for instance the flue gas from a coal-fired power station, through a water-based solution of monoethyl amine or MEA. The liquid absorbs the CO2 from the gas mixture via a reaction with MEA, separating it away from the nitrogen. This CO2-rich solution is then heated, which results in the CO2 being released. The result is a clean and environmentally safe nitrogen gas stream which can be vented into the atmosphere, and a separate CO2 gas stream that can be used in industry, for example in the manufacture of beverages, or stored deep underground, sequestered so that it cannot contribute to global warming.
A CO2 capture plant is typified by the presence of 2 columns, a stripper column and also an absorber column we can see here on my left. Ours are 12 metres tall, about the height of 3 London double-decker buses. Here we are on the ground floor of the plant, and just over here on my left is where we mix the CO2 and nitrogen, which is used to make up the flue gas that we're going to be using in our plant.
It enters the right-hand absorber column here and begins to rise up from the bottom. As the gas rises up the tower, the MEA solution flows down from the top. Along the way, the solution passes over these metal structures called packing that slows the liquid down and spreads it out, maximizing the surface area in which the gas can react with the MEA. By the time the gas stream reaches the top of the column, the CO2 has completely reacted with the MEA. The now CO2-rich amine solution is collected from here and is pumped up to the top of the stripper tower. From there it flows down, passing through these clumps of metal packing which allow the solution to heat efficiently. The heating is provided by the reboiler, where steam is used to heat the liquid to 110 degrees Celsius. The hot MEA solution siphons back into the stripper column. The CO2 vapour then passes up the stripper column to here, where it passes through the condenser. Any MEA solution droplets are condensed, leaving the CO2 as a gas to be collected. The now lean MEA solution leaves through the bottom of the stripper column and is then returned to the start of the cycle.
This brings us to the heart of the system, the ABB control room. From here, the students and the lead learners can actually monitor and control all parts of the plant processes with enormous detail. There are over 250 separate instruments and sensors providing real-time feedback on the operation of the plant, and each of those is monitored here on the extended operator workstations via the ABB 800XA extended automation system. The liquids and gases are flowed using pumps, compressors and blowers, all of which are fully controlled from here. We also have full video and voice communications between the students and the staff working in the control room, and those elsewhere in the pilot plant. Several different communication protocols are used to relay the data from the process instruments, including Ethernet, wireless HART and Foundation Fieldbus, to the control room. On each floor we also have local HMI, or human-machine interface control panels. Here we have a cluster of instruments centered around the inspection port on the absorber column. The instruments measure data like flow rates, temperature and pressure, giving detailed feedback on the process to the control system. With the new ChemEng Discovery Space, we are in an ideal position to give our students real-world experience that will be invaluable in the coming decades. There will be increasing demand for our talented chemical engineers to provide innovative solutions to meet future global environmental challenges. We hope that this new facility will reinforce Imperial College and indeed the UK's role as a leading provider of engineering excellence.